Good morning, afternoon, or evening to everyone, depending on where you're dialing in from. And welcome to this Kisaco research webinar sponsored by Kornami, The Path to Secure Computation, the Revolution in Security. It's my great pleasure to welcome you to this session that we have here today. Joining me, we have our Chief Analyst, Michael Azov, Kornami CEO, Wally Rines, and Program Manager at DARPA, Tom Rondeau. We'll just get into it in just a few moments. We have a short poll as well at the beginning to check everyone's understanding of some of the content that we're going to be discussing today. But before we do that, just a reminder for everyone that I'm sure everyone's done a lot of these things, but please do drop your questions into the Q&A tab. We will be we've got some time at the end to take questions, and we do certainly invite them. So order of service today will be the short poll, followed by Michael, followed by Tom, followed by Wally, and then Q&A at the end. If you're having any sort of technical issues, you can also put that in the Q&A, and we'll try and get to those as well. We have some people in the audience to help with that. But without further ado, we'll get started. So before I hand over to Michael, please, would you take some time to answer this poll? Give you a few seconds to answer this.
All right, thank you, Ed. Welcome, everyone. Thank you for participating in our webinar. I'm Michael Azov, Chief Analyst at Kisaco Research. I work as an industry analyst. I had the pleasure of talking to a lot of experts in this field, and I'm going to paint the landscape for you in my presentation. And then I'll hand over to Tom and Wally, and they're going to talk about their pioneering work in this topic as well. So the landscape, what exactly are we doing? We are trying to secure the whole data lifecycle. So data encryption at rest in storage, that's done. We can encrypt data during transmission down networks, so that's good. But what about when we compute with the data? Normal practice today is to decrypt the data so that we can do various things with it, and that creates vulnerabilities. There could be curiosity from the infrastructure administrators, or there could be insiders and malicious insiders and all kinds of hacking and spyware and malware. Data leaks, and this is what we want to protect. We want to encrypt the data during compute, and we'll talk about technologies that are possible today to do that. We are using at Kisaco the label secure and private compute, but there are other terminologies out there that you may come across. They all mean the same thing: data oblivious computing and privacy preserving computation. So I'm going to mention three main technologies. They're not necessarily head-to-head. They can be used in hybrid manner, and there are other technologies as well. But the three key ones that I'm going to talk about today, the three key ones in this field, first of all, Enclaves Entrusted Execution Environment. So this is a hardware-based in the CPU, Intel software-guarded extensions. Intel SGX was first out, but the others have this technology as well. And basically, you use your public key to encrypt your code and data. You send it to the enclave, and the enclave uses the secret key that's embedded in the hardware of the CPU. So you have to have that edition of the CPU to use TE. SGX is now available on the clouds, public clouds, and we'll see a lot more of this availability. So that's going to be more commonly available. The other key technology is multi-party computation. So this is a task or a requirement. For example, the classic example of 5 millionaires want to know who is the richest amongst them, but none of them want to reveal their individual wealth. So this is what multi-party computation can do. There are various protocols such as secret sharing, and that is, again, one of the key technologies in this field. We're mainly going to talk about in this webinar homomorphic encryption. First of all, there is, I think, misunderstanding as to whether it is Turing complete, and it is. We don't run code in homomorphic encryption. We run our data through circuits, Boolean circuits and arithmetic operations. If you have a computer science background, you'll know that if you can do XOR and the AND gates, the AND operations, then it's Turing complete. And that is what you can do. Addition and multiplication is sufficient Turing complete. So you can build any circuits. But in practice, this technology is better for some applications, especially in numerical computation and others. So it's a question of choosing the right technology for the right application. It is described as a holy grail, fully homomorphic encryption, where it is Turing complete. The other modes for homomorphic encryption somewhat will do as many adds as you want, but only one multiplication. Leveled will only do so many adds and multiplications, and partial additions or multiplications, but not both. And why do we make these distinctions? Well, this is because we are using lattice-based methods, and they add noise. And I'll talk more about the importance of that and how we overcome it in fully homomorphic encryption. But the other thing I want to point out is that this technology is quantum proof, and this is very important. NIST, the US Standards Agency, is going through a competition now to select the next cryptographic standard, and there are no known quantum algorithms to solve this to break this encryption. Apologies for the ringing in the background. If you're familiar with existing standards such as RSA, it's based on solving a hard mathematical problem. We're multiplying two large prime numbers. The public key is based on the multiplication of these two prime numbers, but we can't go the other way. It's very difficult. If you don't know P and Q, you cannot. It's very difficult to find the factors, unless, of course, you have a quantum computing. And this is the problem, that we're trying to get to the point where there are no known algorithms to break our current standards. Now, lattice-based methods, as I mentioned, there is no known quantum algorithm to break this. So this is why this is the one that everyone is now looking at. So this slide shows pictures from the presentation given by Oded Regev, one of the pioneers in lattice-based cryptography. And he shows this lattice, regular lattice on the left. And on the right, we see that we have perturbed one of the points. I've ringed it in a red circle. We've added a bit of noise to move it apart. Now I say to you, which is the nearest lattice point to that perturbed point? And in 2D, it's very easy to see that. Now, Oded, in his lecture, he said, well, what about 500D? And that's very difficult. There's no known method to do that. Whereas Tom, our next speaker, actually pointed out to me that today people are talking about 80,000 dimensions, so even more difficult. So this is where the noise comes in with lattice-based methods. And we're going to try and deal with how to reduce that noise. And this is where Craig Gentry came upon this method that he called bootstrapping in 2009, and this really opened the door to fully homomorphic encryption because it allowed us to reduce the noise. Now, noise, when you're doing the additions in the Boolean circuit that I referred to, is additive, but with multiplication, you'll multiply the noise. That's why multiplication is a serious issue, and why we need something like bootstrapping. So I'm just going to run through exactly how this works at a high level. We're using homomorphic encryption in the green area. So we've got our various data items, D1 to DN. We encrypt it with the FHE protocols, and then we perform our Boolean circuit on it to do the operations. But once we do those additions and multiplications, the noise just increases until it hits a limit. Now, the point about the limit is once the noise goes above that, you can't decrypt it. You can't tell where that yellow point is nearest to that lattice point anymore. It's too difficult to work it out with a decryption key. So the cleverness of bootstrapping is that you wrap the green encoding in the blue one, and then you decrypt the green with its key to get to reduce the noise level, because when you decrypt, the noise is eliminated. And then you continue with the blue scheme, and then you can perform additional bootstrapping as you need it to always reduce your noise level. Now, some of you might say, oh, well, hang on, you've exposed your a secret key because you had to decrypt it. Well, this is where the cleverness comes in, because you actually homomorphically encrypt the green key and tag it to the public key, so it's available in the scheme. And using homomorphic encryption, you can perform operations with the encrypted green key. So it's a really very clever system. So that was the breakthrough. And since 2009, this field has really exploded in terms of research and ideas. And we've got to the point where we have practical systems today. In this high-level chart graph, I've compared the key schemes, and I want to remind you again that these are not necessarily competing head-to-head. You can use them in hybrid methods, and there are other methods as well that we can add on so that we can reduce some of the red areas in there. I want to just focus now on homomorphic encryption, and I've divided it between fully and somewhat and partial. The main thing is that the computation speed is an issue, and we'll talk about that in a second. First, I just want to mention the red areas in homomorphic encryption around confidentiality and integrity, the viewing and the changing of the circuit. For many applications, this is not important. You want to protect the data. With neural networks, you want to protect the parameters and the activation biases of the neural network. You can do that, and so you can have privacy-preserving neural networks with FHE. So it's a question of choosing the right application for this technology. But what I would really want to focus on are two areas. One is the computation speed, and this is where hardware acceleration can make an enormous difference. And this is what Tom and Wally, our next speakers, are going to talk about. And that really brings FHE into real-time application use. And this is why we're using terminology like revolution in security. The other thing I want to point out is that the surface attack size with fully homomorphic encryption is the smallest of these technologies, and that's why it's of such great interest, and why NIST, for example, is looking at the emerging standards based on this technology, and why, if you've got crown jewels, you want to protect it with this technology. So I want to draw a parallel for you with what happened in the AI sphere with deep learning and the explosion of AI chips on the market to accelerate that. This is an example of the chips that appeared at Kisaco's AI Hardware Summit. We expect that there's going to be this level of activity for accelerating FHE and bringing it to real-time application use. So great opportunity for our next speakers, and that's me done, so thank you. And I believe we're going to see the poll results. Is that right, Ed?
Yes.
Oh, right, so here we are, 35%, so that's a really, a third, that's a very good number that are active in homomorphic encryption. So that's really more than I expect. I'll let Tom and Wally also comment on these results.
Interesting poll results, kind of encouraging. And also, since we at DARPA started going down this path with this new program called Data Protection in Virtual Environments, or DPRIVE as our acronym spells out there, you know, this is it's a fairly new field. You know, you mentioned Craig Gentry. You know, that was a 2009 PhD dissertation. So the revolution here, you know, is 11-ish years old, despite the theory for decades that this is possible. So to see that there are so many people there already looking at this. I mean, this is how fast the world can change, I think. So that's very interesting and encouraging. And I think it puts us in a very good place here for what we're doing at DARPA. So for those who don't know, I'm Tom Rondo. I'm a program manager at the Defense Advanced Research Projects Agency. We are a U.S. Department of Defense agency tasked with fundamental breakthroughs and preventing strategic surprise. So we go after very hard problems and try to invent things for strategic purposes as faster than anybody else. Trying to keep our finger on the trends and see what we can do to address really difficult problems. And this is to me a perfect one. I'll get into some of the history in a second, but to restate, kind of put in some terms that I've been thinking about this challenge in. To restate what Michael had already said, we all know that the problem today. I think that's why homomorphic encryption and why those poll results were so positive in this case. The amount of data that's out there, the amount of data that we have to protect in the world continues to grow. The challenges of cybersecurities, criminals, nation-state threats, rogue nation threats. All of those have been weighing on all of us, and of course within the DoD and the U.S. government, we especially take this seriously. So you can just look at the laundry list of areas of places where data is available, data is representing us, ourselves. And so this quote, this is one of my favorite films of all time, Sneakers from 1992. Ben Kingsley's character as Cosmo has this quote, "The world isn't run by weapons anymore or energy or money. It's run by little ones and zeros, little bits of data. It's all just electrons." And that's always spoken to me, even before anybody knew what the World Wide Web was, or very few people did. What was going on in the internet revolution back at the time, they were, this was in the atmosphere. And I think it's very true. It's more true today than it was back then. And continuing to think about it from a Department of Defense perspective, this is this kind of perspective is really why we start thinking about this instead of the traditional big weapons. And so to wrap it around to the title of the slide, money makes the world go round. The old cabaret song that always gets stuck in my head. But now we're thinking about a world where data makes the world go round. And so that provides a really significant threat, a really significant opportunity for us if we know how to handle it properly. Again, Michael's gone over this, but just to kind of, again, wrap it up in a different light, what we're talking about here is the problem of protecting data at all times. If you have valuable data, so again, taking images from the film Sneakers, this is like the power grid, unencrypted data, very important, valuable data. You want to protect that, so you wrap it through some encrypted process, some complex math, and the mathematical proofs of encryption are pretty young in terms of the history of mathematics. Really kind of came to the forefront in World War II. We've been going crazy with it ever since. So they become more and more complicated and complex here, so that by the time you're done with this encryption process, you have just this blob of data sitting unusable, unreadable by anybody else, unless you have the secret key, or in this case of Sneakers, a magical decryption device that can break anything. You pass it through that decryption device with your secret key, and you get your data back out. But now, of course, it's back in a vulnerable spot. So now if it's sitting on a server somewhere, it's sitting with some advanced persistent threat. Somebody is resident on that computer, think Spectre, Meltdown, those types of situations. That's computing on unencrypted data. That's now vulnerable in a threat. FHE allows us to compute on encrypted data, which means we don't have to decrypt it in this process to do computations. That's the value proposition here of keeping our data protected at all times. So what we're doing in the Deprived program, the reason why we kicked this off is this math, as I mentioned, Craig Gentry kind of exploded this space in 2009 by understanding how to use lattice cryptography in a way that allows us to do fully homomorphic and this Turing complete circuits. But it's so computationally expensive. And DARPA ran a program a few years ago called Proceed. and Drew Dean created and ran that program, and they really knocked down a lot of the challenges from the security, the understanding of the security posture, to the algorithms, to the software implementation of how you code in fully homomorphic encryption. And so today, that graph on the right-hand side shows you kind of where we are as far as a computational challenge today. So we just did an analysis of a simple convolutional neural network. How do you run an inference in that system? And today's FHE is showing you in terms of billions of seconds to do what will be a fairly simple operation today. Whereas if we had unencrypted processing, or if we were just operating on the plain text of that space, you can do it in milliseconds. So what Deprive is looking at is how do we take those million X challenge of computation into something that's really digestible. So we're kind of aiming to be within effectively spitting distance of plain text processing. Insights and the analysis that we did to get us to where we think we can achieve this, the goal of the Deprive program by building a hardware accelerator, came from some ideas of better data structures, data processing approaches and architectures. This large arithmetic word size allows us to compute in the native space of the lattice cryptography that instead of doing a lot of transforms. Some of that was some of the inspiration there. A lot of really good ideas for how to overcome this gap here, and that's what the Deprive program is about. So we're also trying to make sure that we have a programmable system so we can keep up with the parameter space changes, the algorithm changes, all of that to create this, continue to involve and invest in this in the FHE space. So we're building in the Deprive program, we're building silicon approaches to address this problem in different ways and to try to hit various program metrics that we define into the Deprive program. So new chip architectures, flexible data structures, programming models, all of these designed to help us meet these goals. So for the kind of wrap up here, the way that I thought about this program and really where the inspiration came from, the Deprive program name, in fact, right? We talked about data protection. The virtual environments was one of the biggest inspirations here, thinking about the future, the current space of virtual networking and virtual machines of the cloud, and then virtual networking of 5G and future cellular standards. The amount of data that we're going to be storing, that we're going to be generating, we're going to be moving across and computing against in this future virtualized world, kind of codified in these two spaces here, those were what drove me to think, well, how can we approach solving these issues? Not just using FHE for some of the things that Wally talked about, where we're using it today for some really critical problems. How can we start to drive it towards where we can use this for more potentially in the future, all computational problems to continuously protect our data. So really, we're trying to deprive the bad guy from ever being able to see, manipulate, control our data, and therefore potentially control us in the process. So that's what the Deprive program is going after here. We're also trying to engage in a much bigger context, looking at between the defense, the commercial industry, looking at it from the standards perspective of how do we interface with networking wireless standards, how do we make sure that we're building towards a kind of a larger harmonious approach to solving this problem at a worldwide scale where everybody can take advantage of this. That's really part of the goal here. And so I'm really happy to announce we now have all of our performers under contract. We will have a program kickoff in a month. But so we have 4 performers that we selected for the program. We'll be working with Intel. Second one is Galois, SRI, and Duality that was already mentioned. So from small business to research focus to DoD focus to consumer and industrial applications, we're really going after a fairly wide approach to this, and they're all coming at us with different ideas and different architecture approaches that we're really going to be able to work on through the course of this 4-year program. So really excited that I could actually announce that today as we're now ready to go. And with that, I'm going to finish up my prepared remarks.
Advances in technology, in economies, and in the world depend upon the ability to productively share information. And the emergence of artificial intelligence and machine learning is providing new insights, new inventions when it's applied to megadata. How big is the megadata we're looking at? Really big. 2.5 quintillion bytes of data every day. And by most estimates, only a small fraction, a few percentage, is actually analyzed for productive purposes. And yet we hear from a lot of people that data is the new oil. It contains all of the know-how that humanity has developed, all the insights into the future, and can be monetized to create wealth as we move forward. That monetization creates value for individuals and corporations as they put it together, but they need to be able to sell it, to charge for it without divulging it. Machine learning models are extremely valuable, but they cost a lot to prepare. They have a lot of expertise. And fully homomorphic encryption is a way that this data can be monetized. But we're also under a lot of pressure for privacy and confidentiality of data, the GDPR regulations, and there's also a great increase in cybercrime. How much money? Well, GDPR penalties are getting bigger, tens of millions of dollars for individual charges. And on the projections for the future, some estimate that cybercrime alone will cost in the trillions of dollars this year. On top of that, the number of attacks has increased, 240% increase in the cyber attacks on banks. And so protection becomes even more important. Well, fully homomorphic encryption is the ultimate solution for cybersecurity. I was doing some work for DARPA for Tom Rondeau, and he asked me to survey the semiconductor industry and find out who's actually working on chips that could enable the kind of compute capability that FHE would require. I did that. The companies I talked to, which represent a cross-section of the industry, all told me we're at least 5 years and probably 10 years away from anything practical. Certainly for real-time fully homomorphic encryption, it would require 1 million times the performance of today's best computers. It just isn't going to happen. I reported back to Tom, and he created the Deprived program and then went on my way. But then I encountered Kornami. And at Kornami, I found that incidentally, they had almost accidentally developed a capability. Now, the U.S. Department of Defense has a zero trust assumption. They assume that data centers have been compromised, the operating systems, the chips themselves, all compromised. And so there's only one path for sensitive data, and that is, in fact, the use of fully homomorphic encryption. Tom has taken a lead in driving the industry, and it's been extremely fortunate for me. It's changed my life when I encountered Kornami. Now, as has been said, fully homomorphic encryption means that you can encrypt your data and then send it to insecure places, untrusted compute environments, and the key is never revealed. It stays encrypted. And so the calculations are performed on the encrypted data, and the encrypted results are sent back. Where's it going to impact? Well, we've already said the Department of Defense is anxious to move quickly, but I find that the financial community is more anxious, in fact, and will move quickly. Most fintech companies, investment banks, insurance companies, and others have some level of homomorphic encryption activity already. Healthcare companies, those collecting sensitive healthcare data or building diagnostic models, all have a vested interest in being able to use encrypted data. And there are a variety of other applications. So we can imagine a point in the future where if you build a machine learning model and train it, then by encrypting it with FHE encryption, you can market it. People never see the data. They cannot reverse engineer the coefficients in a neural network, and it becomes a business. Now, the machine learning market for software and services is expected to reach $20 billion by 2024. There is one minor problem, as we've said. It requires about 1 million times the performance of today's best Xeon servers in order to achieve real time. It may be useful at less than that, but real time is a long way away. The reason? The processing challenge is awesome. An example of a customer case we ran at Kornami, just to do a simple AND gate. The inputs, A and B, are converted into 500 order polynomials with double precision floating point coefficients. And to do the calculation, it's necessary to do 3,000 1,000 point complex 64-bit floating point fast Fourier transforms. A lot of computation, really awesome. Well, it turns out that in developing an AI processor, Kornami, over a period of almost 10 years, had developed the basic keys to also do fully homomorphic encryption. They also developed an emulator for the chip they've designed so they can do metrics of how well will the chip perform. The major initial accomplishment was the TrueStream compiler, which can take the source code or can take the operators from FHE or the operators from any framework like Onyx or PyTorch or TensorFlow, and it can separate the source into independent streams of data and control, which can be processed in parallel on multi-core computers. With TrueStream, then any computer can be accelerated, but Kornami decided to design a chip that took full advantage of that, built with systolic arrays to stream the data without intermediate storage or with minimal intermediate storage, and a compute fabric that, because of a network on chip, scales across chips, across boards, and across servers. The more chips you add to the system, the higher the performance. The chips have dynamic reconfigurability, so they can be modified to fit the shape of the algorithm. And using an innovation from DARPA, the large arithmetic word size, you can achieve real-time, all 10 to the 6th x performance with the initial chips, which are expected early next year. So how did Kornami do that? Well, the architecture is made up of identical cores. Each core can perform all of the forms of computation required and can be reconfigured to perform different functions. These cores are put together, thousands of cores per chip, and then multiple chips per board. And as a result of the TrueStream compiler, you're able to take the source code and run it very rapidly and achieve the requirements. Well, how quickly is the world going to adopt this as chips become available in the coming years? And I think the answer is very fast. You've already seen homomorphic encryption used in the 2020 election with the Microsoft Election Guard, and you've seen the anxious moves by the Department of Defense. There are hundreds of companies that already have homomorphic encryption programs, and Gartner estimates that by 2025, 25% of all companies will have homomorphic encryption programs. As I mentioned, machine learning is big business, and this is a way to do it very profitably and to protect the data developed. And there are lots of companies, ones that Tom will mention, like Duality, Infer, Enveil, Cosmian, all helping customers to use homomorphic encryption. Well, Kornami had developed its compiler and largely completed the chip design and had their emulator running. And they were approached by a Fortune 50, actually, customer who is dedicated to ramping up fully homomorphic encryption very rapidly. And they had developed benchmarks and other applications, and they brought one to Kornami that they had run on Intel servers and multi-core servers. They actually used 12.5 racks on the AWS, and that added up to 24,000 Intel cores. And their test set of 100 million data entries with lots of operations took 4.4 days. So Kornami ran that on their emulator, and the net result, if they used as many racks as the Intel ones, was 10 seconds. The company didn't really need that. They needed 10 minutes. You can do that with 16 one-use servers with the first generation Kornami part. So with that, they became anxious to ramp up the capability quickly, and we expect them to be one of our early customers. Well, actually, fully homomorphic encryption is arriving just in time. The quantum computers, as you've heard, will break most internet security. By some estimates, when you get to 1,000 qubits, most of the security breaks down, but not fully homomorphic encryption. And it's hopeful, I think it's likely to be expected that we'll have available reasonable performance fully homomorphic encryption by that time. So to summarize, our global future depends upon our ability to collaborate. FHE makes data sharing and analytics possible without ever revealing the data. Computing limitations for FHE are being rapidly overcome, and the regulations, liabilities, and business opportunities will drive rapid FHE adoption as compute fabrics become available in the next few years.
So I'm going to kick us off with the Q&A. We've had lots coming in already, far more than we'll be able to get to, but I'll kick us off with question 1. So what is the end game in this field? How will IT change, and how will people think about data? We start with you, Michael.
Okay. All right. So end game, I think we can expect, in the same way that when you send information on the internet, and today we now use HTTPS, so we encrypt our data when we transmit it. I believe that there will be a point where we will be ubiquitously working with encrypted data. So that is the end game, where it's ubiquitous, it's seamless, it's available everywhere, and that gives us maximum protection. So that is the end game.
Okay, thank you, Wally.
Oh, well,
anything to add to that?
Well, I think it's if you ask a customer, do you at the same price would you rather have a secure server or an insecure one? I think it's a fairly easy sales proposition, and so I think initially it will come to people that are whose data is highly sensitive, but I think over time, potentially more and more of the server infrastructure in the world will move toward a capability to process fully homomorphic encrypted data.
Okay, great. Anything to add there, Tom?
Yeah, I can't disagree with any of that. I'm looking at this, as I just mentioned in my remarks there, I'm looking at this from the holistic view of where this impacts. And we are focused, we are DARPA, there is a big D in our name. We are focused on defense and Defense Department and our role here. So protecting our data is, of course, of paramount interest to us. We go through exorbitant amount of work to secure our data, to protect our data. To try to do that at all parts of the puzzle is really important for our operations and our long-term strategies within the DoD. I look at the protection of data from that perspective, and then the ability to actually do that effectively, I have to widen my aperture and say that this is a benefit to the entire United States, and frankly, I think it's a benefit to the world, to enable us to protect our data everywhere. And it means that we're all working off of the same advances in the research, advances in the silicon, as we're doing in the program, and the algorithms in mathematics, so that we can continuously benefit and trade back and forth. So we have the most robust perspective, the most robust systems. And as we build these into our networks and into our virtual systems, it just benefits everybody, and it benefits us directly to have that as a kind of a commoditized way of protecting data. So yeah, the vision here is that it goes everywhere. How it gets staged, I think Wally's got a very good perspective on that as far as the staging of the rolling out of this and where it's going to impact first. But I do see a future where we could be looking at this in all sorts of, almost every application you could conceive of.
Thanks very much. There are so many questions coming in. I just want to tell everyone, if your question doesn't get answered, we'll make sure that we reach out to you via email to answer these after the show. I'm going to pick one out here. If you could only pick one, which is the bigger bottleneck to FHE adoption, hardware or software?
Well, I think clearly from what we've been talking about, the computation time without hardware acceleration is clearly the bottleneck. And this is what Kornami is trying to do and what DARPA is trying to do. We're trying to get to the point where FHE is possible in real time. So at the moment, without the acceleration, that is the bottleneck, the computation time. Yep.
I'll jump in. I think they do go hand in hand in a way. And the whole idea for me of building hardware to accelerate that is so that the innovations can actually happen faster in the software world. Nothing gets adopted without the ability to program on it. No silicon actually gets adopted, gets commercialized. Well, get commercialized, doesn't get sold without software supporting the ability to program on it. But then the innovation space, we're still, as we mentioned, it's an 11, 12-year-old idea. Some of the core algorithms, some of the core software tools are years old, right? They're babies in the math and the encryption domain. But it's hard to accelerate when you have to wait 15 years to answer a question. If you can do that at speed, we build an aircraft, fighter jet. It takes us decades. You build a chip, it takes you years. You build an FPGA program, it takes you days. You can compile and you can execute on Python code or in C++. You can innovate. The innovation cycle just starts to spiral the more you can compress your time. That's what I think. So the enabler here is the hardware. The vision here is how you actually support that entire software ecosystem.
Yeah, I think the hardware is the enabler. We have to get to a minimum level of performance before people put in the effort to do the any ports they need to do. And I think one of the great things about the DPRIVE program is clearly if you're within an order of magnitude, then that raises a flag and people start working very hard. Of course, Kornami intends to take it further, but it doesn't have to be further to motivate people to move their software.
Okay. Great. There's been a couple of questions in the vein of quantum machine learning. If it's possible, will this be a threat to FHE in the future? Well,
I think that the current state of expertise is that there isn't a known quantum algorithm that will run on a quantum computer that will crack the lattice-based methods. So this is why these methods have been selected. And I think there was another question about using other methods in homomorphic encryption. But the whole point is that they have concentrated on lattice-based methods because they are so solid and quantum proof. Who is to say in the future? But this is where I ask the experts, and that's what they tell me.
Yeah, and I'll jump in here. I'm going to go a little bit math and technical, but the math joke in heavy quotations there is we're only concerned about lattice cryptography from a quantum sense if P equals NP. So the space that we're talking about here is that lattice crypto, the solution to lattice crypto, the shortest vector problem is an NP hard problem. Quantum computers are not good at NP hard problems. That's the key in kind of context there is if you look at decidability problems in the P versus NP space, this sits in a spot that quantum computers aren't good at. It's a misconception that quantum computers are just classical computers that go faster. They're good at certain classes of problems, not every problem. And lattice is, as Michael said, it's not guaranteed, but in how we understand how quantum computers approach solving certain problems, the shortest vector problem does not fit into that space. And therefore, it's not that we don't know how to do it. We don't think it can be done unless there's this real innovation and a breakthrough in the mathematics of what we can conceive of in quantum. Or if P equals NP, and therefore an NP hard problem can be solved in polynomial time, and then we're all screwed.
I think that covers it well.
Okay, great. This one's specifically for you, Wally. So just a question about what's next for Kornami in the next 6 months or so, 6 to 12 months. Some of the, you're looking at companies in the space that have complementary products that you'd like to partner up with, and a follow-on question about the trade-offs in your technology products. What are some of the things that you're facing at the moment in your product development?
Yes. So as I mentioned, over a period of a number of years, the compiler technology was developed, and then the chip was designed over the last couple years. That design was functionality was frozen about a year ago, and so it's been in verification ever since. It's coming to the late stages of verification, and so we'll be releasing our first PG tape during later in the year, and then we have partnerships with Mini Computer Company. We have for servers and boards. We have a partnership with actually Infer, the one of the companies that works with customers on homomorphic encryption, and so we'll be providing at all levels, and in addition, some of our own support for the early adopters. We'll have a development system that supports people who want to test it out, try out their applications, and all of that. I think we'll get into full gear next year.
Mm-hmm. Okay. Another one specific to Kornami. How would you compare the value prop of Kornami to Intel Dpdk? Anything you can speak about the fungibility guarantees that Kornami provides?
Okay. Well, so I would say that the fully homomorphic encryption is an orthogonal vector to all these. So fungible methods, actually, Kornami can act as a coprocessor in an Intel environment. And I think if you look at the general architecture of x86, it does MIMD well, multiple instruction, multiple data, and there have been extensions to help work with SIMD. The Kornami adds the dimensions of pipelining and systolic arrays to the performance. So as a complement to an Intel server, very valuable, having a server center that has both Kornami for the FHE processing and conventional computers for other types of processing, in much the way that you use NVIDIA servers in an Intel environment. That's another valuable one. And the last one is chiplets, the ability to take, for example, a Kornami processor and put it in the same package with an x86 server. Those are all possibilities that can evolve as the world demands the protections that FHE provides.
Mm-hmm. Thank you. An interesting one here. Are you taking into account the explosion of data size upon encryption? There's approximately a 10 to the power of 6x explosion in data size. Communication bandwidth could be a bottleneck here as well.
Oh gosh, well, I don't know who wants to take that, but I think with the growth of data, there is a growth in computation capability to deal with it, and various methods, such as working at the edge. There's a whole host of means and ways of working with data. I think it's a slightly different problem. What we're concerned here is protecting the data, and that is possible with this technology. We really need to have the accelerators to make it real time and deal with a data explosion as well. But yeah, I'll let Tom and Wally step in as well.
Yeah. Well, Michael, I think the question really is not so much data explosion in the world, which is happening as you addressed, but even when you encrypt something into a fully homomorphic encryption space, you actually explode. The crypto side, the ciphertext is orders of magnitude larger than the plain text. So now you actually have which is something we explicitly have created within the private program. That was one of the key challenges in our, what we call a broad agency announcement. That's how we announce a program and people propose against that. One of the key challenges was the memory management and the interconnect overhead, which is why we think building it into an ASIC is important versus trying to just span this across a cloud infrastructure because of that the interconnect bottleneck. cache sizes, how do you actually manage cache? Frankly, how do you do cache prediction if you can't read the data? So things like that were intimately tied into our program. So yes, we're very aware of that challenge. And then just assuming that challenge continues to exist, as it looks like it does within the FHE algorithms. And by the way, we're using specifically BGB as our challenge problem. I know there's plenty of other types of algorithms out there. They're all roughly related to the same lattice-based crypto space, just kind of how you implement it. BGB has just been knocked around long enough that we felt safe that can be our core challenge space. But this parameterization that I mentioned, I'm not sure where I cut off on that slide, but we wanted to make sure it was parameterizable because there are innovations coming along in the algorithm world. There are new inventions in FHE that are talking about a much smaller crypto size explosion. I think Craig has said there's a 1-for-1. Lots of work needs to be gone into understanding what that actually means for security of it. But so while we're trying to prepare our chips for that, we're also trying to make sure that we're tracking the innovations in the space to try to control that explosion.
Yeah, and in overcoming those problems, I think to handle the massive amount of data that is in fact generated in the process, it's been evident to us that you just can't afford all the caching and memory accesses that exist in traditional von Neumann architectures. You need to be able to stream the data, and with that, since most of the power dissipation in advanced neuromorphic computing chips today comes from memory reads and writes, avoid those memory reads and writes, stream the data through, and that's how Kornami's, based on the emulation results, that's how Kornami has been able to achieve such a low power and still get to the kind of performance that's required for real-time FHE.
Mm-hmm. Okay, thank you. Thank you. Well, I think we've probably got time for one more. The remaining 27 questions will have to be answered via email after the show. So this one seemed very interesting. So do you see a time where fully homomorphic encryption can be implemented in endpoint devices, PCs, phones, etc.? Or will this only ever be implemented at the data center level?
Yeah, we believe there will be a market at the edge as well. I think the cost sensitivity of a lot of edge node applications will delay it for some time. But in fundamental principle, there's no reason why it can't be at the edge as well as in the cloud.
I concur.
Would you speak sorry, Tom.
Yeah, I'll be quick. I concur with that. We have a mind towards that, but my program was not specifically trying to get power. We didn't have a power or performance per power metric to hit because we wanted to make sure that we can understand the algorithm space and actually mapping it to the silicon appropriately. But I think that there's probably a future where taking some of these innovations we'll discover over the next few years so that we can actually build it into edge computing.
Yeah,
okay,
and
so
just to add that this is a driver for moving away from von Neumann architectures. The benefit of having a secure compute everywhere, cloud and on the edge. So I think this is one of the things that will push towards those pioneering technologies.
Okay, great. So just to wrap us up, Wally, would you speak a little bit you mentioned cost. There's been a couple of questions around cost. Can you shed some light on that aspect of this technology?
Yeah, I think we can see our way to costs that are in the same range as special purpose servers today, NVIDIA-based servers, for example. It won't start out that way, but I think it will move closely enough and people will be able to see the vector so that really the trade-off will become less and less difficult for people when they can run at the same speed as processing plain text and do it at the same or a modestly greater cost. That will spur the adoption.
Any other thoughts from the other panelists?
Yeah, I guess just from our perspective, DARPA, we invest in early research. We're investing in what we call the non-recurring engineering bits of this. We buy down a lot of those challenges so that when we're done with this, we'll have what look like fairly large silicon chips, but still, based on today's silicon processes, 10, 7, maybe 5 nanometers. So advanced nodes today, but we're still just basing them off of current silicon. So no invention of materials, no challenges there. So if we, like I said, bite off a lot of that, then yes, I think we can get to a point where the chips become relatively cost effective. The power, if we can pull that down, so the operational expenses start to get minimized as we start to close this performance gap. So yeah, I hope that we see ourselves towards a future where we can buy this down.
Great. Thank you so much. And with that, we're out of time. So I'll thank our panelists. Thank you, Michael. Thank you, Tom. Thank you, Wally. And many thanks to Kornami for hosting this for us. We hope to see you again soon, everyone. And I hope we've left you with the impression that the path to secure computation might be a little bit shorter than you think. So with that, thank you to everyone, and enjoy the rest of your days.
Thank you, Ed.
Appreciate it.
Thanks a lot. Bye-bye.
Bye.